if you recollect, we were talking about frequency translation and mixing, and in particular we were looking at the effect of the situation effect in a situation where a local oscillator is used to translate the incoming signal carrier frequency from a value omega 1 to some value omega 2, right. And we said that we could do this by choosing a local oscillator at frequency omega 1 plus omega 2 or omega 1 minus omega 2. However, when we do that, we also found there is a small problem which we have to keep in mind, and the problem is that of the image frequency, right. The image frequency will also get translated to the same output frequency. So, if the input is omega 1, output is at omega 2, the local oscillator is omega 1 plus omega 2. If the input is omega 1 plus 2 omega 2 with the same local oscillator frequency, you will again get an output frequency which is omega 2. Therefore, omega 1 plus 2 omega 2 is the image frequency corresponding to omega 1, right. Similarly, omega 1 minus 2 omega 2 will be the image frequency if the local oscillator had a frequency of omega 1 minus omega 2, right. So, that is basically what we learned, the concept of image frequency. So, that is a brief review of what we did last time. Today we will look at the application of this in designing what is called a super heterodyne receiver, right. In short, sometimes known as Superhet receiver, but basically it is a super heterodyne receiver. As to what heterodyning means, we already know. Why do we use the prefix super is something that we will learn today after finding out what this receiver is all about. Okay, let us discuss what do we want a typical broadcast receiver or any other kind of receiver which has to tune itself, which has to receive signals not necessarily at a single carrier frequency, but from a range of carrier frequencies in a certain band of operation, right. That is going to be typically the case. The receiver is not going to be designed to operate at a single carrier frequency. You are going to fix a band of frequencies from which signals could be received, and multiple sources of information could be available, and you may like to tune into any one of those sources of information. That is what you would like to have. When you want to have a when you want to deal with a requirement like this, you need to design a receiver which can tune itself properly and give us some of the things that we want, right. Now, what are the things that we want? Let us from a good receiver, suppose we were to try to enumerate a few important features that it should have in this kind of situation. From common sense, can we figure out 1, 2, 3 number of criteria which this receiver should satisfy? Can you make any suggestions? First thing is that it should be frequency selective, right. That is basically what is meant by tuning. But more importantly, what is meant by this term is that if there are two radio stations, if there are two transmitting stations at close by carrier frequencies, I should be able to reject one and accept the other. I should be able to accept one without having interference from the closely spaced frequency, right. So, it should be frequency selective enough to reject a closed carrier frequency, right. So, it should be frequency selective. Selectivity therefore is one very important criterion in receiver design. The second is you would like that even the weak signals are captured nicely, right. So, even if a signal is coming from a transmitting station which is far off, and therefore the signal strength at the receiver antenna is small, you would like that it be captured nicely, right, and therefore that property we call sensitivity, right. It should be sensitive to weak signals. You should have good sensitivity, right. Even weak signals should be possible to acquire. And of course, the most important thing is in all these situations the basic message signal should not get distorted, right. The output message signal at the receiver finally that you hear or that you see, depending on whether you are hearing something or seeing something, should be as close a replica of the transmitted message as possible, right, and that is referred to as fidelity, right. So these are the three important properties that any good receiver will have. It should be highly selective, it should be sensitive to weak signals, and it should have a good fidelity, right. So for example, you talk about high fidelity systems, right. So a receiver should be a high fidelity system. It should produce a very good replica of the actual message, right, without any distortion. There should be very small amount of distortion, if any. Now let us look at these issues now. How can we achieve all this, right? The important let us discuss, let us say, one of these problems and see why it is not easy to achieve this unless you do something clever, right. Take for example frequency selectivity. Frequency selectivity and these two things, high frequency selectivity and these two other properties, it is very difficult for these to go together. If you for example try to achieve all the selectivity directly at the input to the receiver, right. So I mean the first reaction is that a receiver front end should be a filter, a tunable filter, which you can tune to any frequency, right. That is the most obvious solution to having a receiver which can tune into a whole band of frequencies, right. So obviously you should have at the front end of the receiver you should have a filter which will allow the passage of only a single carrier frequency and the message around that, right. The message bandwidth, let us say, suppose it is a music signal that you are looking at, voice or music signal, the bandwidth is going to be about 15 kilohertz, not more than that, right. So let us say you are operating at a frequency of 1 megahertz. So you want a selectivity such that the bandwidth is about 15 kilohertz with a center frequency of 1 megahertz. Not only that, so if it was a fixed center frequency, a fixed bandwidth, this specification 15 kilohertz bandwidth at 1 megahertz makes the Q pretty high. The quality factor of such a tuned circuit is quite high if you compute it, right. How much is it? It is 1000 divided by 15, right, which is of the order of how much? About 60 or 70. It is a fairly high Q, right. Now the difficulty, right, this Q is achievable with fairly complex circuitry, but this Q, when you want the circuit also to be tunable, right, when the carrier frequency has to be adjustable, is a very difficult thing to achieve, right. When this carrier frequency, let us say, has to be adjustable across the whole AM band that you are operating in, right. So it may go from, let us say, 500 kilohertz to 1500 kilohertz. Very difficult to achieve such a high Q, such a high selectivity while having this tuning option. Very difficult to have this in terms of practical filters. So difficult to realize, it is very difficult to realize highly frequency selective filters which are also tunable. Over the band. As I say, you can't have everything in life, isn't it? Same thing here. Not only that, if you want sensitivity, good sensitivity, what do you want this? You should not just do filtering operation. You should provide a large gain so that a weak signal is strengthened, right? Sensitivity means how can you achieve sensitivity? By having a large gain in the receiver. So it should actually be an RF amplifier which is tunable, right, highly frequency selective, and provides you high gain. Now, these are, if you have all these ingredients in the RF amplifier, you are bound to most probably generate an oscillator and not when you try to realize it rather than an amplifier, because these are the prescriptions of an unstable amplifier. High gain associated with high frequency selectivity, etc., will typically generate conditions which will be very difficult to control. Your parasitic capacitances and your various other elements in the circuit will make it highly unstable. It will be very difficult to realize such a tuned filter which provides you all these things, right. Of course, fidelity would simply require that the bandwidth of the filter should be sufficient to pass the message without distortion, right. So, if it is a 15 kilohertz bandwidth signal, over the 15 kilohertz you do not have a lot of variation in the frequency response of the filter, either in amplitude or in phase. Of course, phase distortion is not very important in voice applications, in music applications, but it is fairly important in let us say TV applications, picture applications. So,
noise will also be amplified.
That is true. The question is, if the sensitivity is increased, it will also increase the response to the noise, right? True, but ultimately what matters is the signal to noise ratio, right? So, for that you want to make sure that only that portion of the spectrum is allowed to pass through which carries the message signal, right. That is why they have to be selective. The selectivity is also required not only to avoid interference from other sources, other transmissions, but also to ensure that too much noise does not come through, because noise is typically is distributed equally at all frequencies. So, you only want to live with that amount of noise which is inescapable, right. So, frequency selectivity will take care of that to some extent, right. So, the other points therefore that I made are that tunable filters of this kind also cannot easily be made. If you pay a price, you can always get everything that you want, but you have to pay a very heavy price in that case. Cannot easily be made to be highly sensitive or let us say with high fidelity. So, these are the problems. This is not a key problem, but this is definitely a problem, right. So, tunable filters cannot be made highly selective, they cannot be made highly sensitive, and these are the requirements that you would like to have in a receiver, right. So, how do you achieve these requirements then? What is the alternative? Can you think of a clever solution? The hint is that the discussion that we had last time about frequency translation and mixing should provide us a solution. Can a solution come from the floor? What feature should we remove in this slightly bleak picture so that these disadvantages go away?
So we can have the amplifier designed such that it amplifies one particular frequency very well, and then translate the signal we want to be amplified to that particular frequency.
Very good. That's basically the idea. You translate every single frequency that comes in, any carrier frequency in which you are interested, after tuning into that, onto a single fixed frequency, right? And the features that you want, selectivity, sensitivity and fidelity, should be features of this fixed frequency tuned filter rather than a variable frequency tuned filter, right? That is the answer to our question, right? So, the answer is the solution to this problem is achieve or try to achieve these three properties by converting any incoming frequency of interest by frequency. Here I mean carrier frequency, it is implied, right? There is a message along with its carrier frequency, right? by incoming frequency of interest to a fixed frequency, right. This is at this frequency, as the receiver carries out most of its nice jobs that it has to do at this fixed frequency, and it is typically known by the name of intermediate frequency, or in short IF, right. Last time I put IF for image frequency, but IF is more commonly used for intermediate frequency, and therefore a typical receiver picture.
So how do we select from this?
I am giving the details now. Let me go through the process, and then I think if there are any questions after that, we will take care of that. So the super heterodyne receiver precisely does that. You have your signal coming in from your antenna. The first stage has to be the radio frequency stage, which carries out the initial filtering. So this is the radio frequency filter and maybe some amplification. So remember that filtering has to be done for two reasons: one, to reject other signals, and the other to remove noise, out of band noise, right? Noise which does not lie in the message bandwidth. The noise that lies in the message bandwidth, you can't do really very much about it. It has to come along with the signal. Now this signal, now therefore, so you have tuned it to certain frequency, right? May not be very highly frequency selective at the moment, because we are saying that selectivity will put somewhere else, right? But you are roughly tuned it to the frequency of interest, right? And what should you do? You should convert this signal now to an intermediate frequency signal. So this is like the frequency translation we were discussing yesterday by using a mixer, right? And a mixer will have two inputs, one the incoming signal here and a local oscillator, right? So this mixer, which is again a multiplier, right, takes the other input from a local oscillator whose frequency is, suppose this is omega c, right, this will be omega c plus minus omega if, right. If it is omega, so that the converted frequency is omega if, right. And now no matter what is, whatever the input signal here, this will always be omega if. The output here will always be at omega if. Of course, you will have to make sure that these two things, the filter and amplifier combination here and the local oscillator here, they are tuned together, so that if this you tune this to a different frequency, this also generates a different frequency, right. If this goes from omega 1 to omega 2, this will also this should change from omega 1 plus omega if to omega 2 plus omega if. As this is tuned, this also should tune. So this tuning is typically ganged up, right. This happens together through a single ganged up set of capacitors or whatever. In fact, if any of you who is familiar with or who has ever opened a radio set, you will see a set of parallel plate capacitors which are ganged up together. There are two sets of plates, and when you do tuning, basically both the set of capacitors, they move in and out, right. So that ganging up is done to change both the local oscillator frequency as well as the center frequency of the tune filter here, so that the difference between these two frequencies is always omega if, right. So that has to be done. So this is now passed through an IF amplifier, right, and it is this amplifier which provides all the nice properties that you want from the receiver. You can make it frequency selective, its bandwidth can be exactly 15 kilohertz, no more no less. Typically if you are providing for a bandwidth of 15 kilohertz in a radio receiver, the different transmitting stations would have frequency separation of about 20 kilohertz or 25 kilohertz, right. So you want to make sure that an adjacent signal which may be 25 kilohertz away does not come out at the input of the IF amplifier, is rejected, right. So that kind of selectivity can be provided by the IF amplifier. Excuse me. Similarly, the IF amplifier can provide you high gain, right, because if this is at a fixed frequency, realizing such an amplifier with high gain is not a problem, right. And of course it can give you the fidelity that you want. Of course fidelity, most of the fidelity problems arise not at this stage, but they arise at the power amplifier stage, which typically follows this, right, after you have detected the signal, right. So anyway, the nature, let me complete, the nature of the signal here and the signal that was coming in, they are identical. All you have done is translated the signal, the modulated signal from omega c to omega if, right. So you again get an amplitude modulated signal here, except that the carrier frequency is no longer omega c, but the carrier frequency is omega if. So after this you have to do the demodulation, which you can use, for which you can use whatever you would like to use. Typically in this kind of an application, it is an envelope detector followed by a power amplifier, which is where most of the distortions are likely to arise, because now you have the message signal here which you want to power amplify before you drive into a speaker or whatever display device you have, right, output device you have, and this can go to, let us say if it is voice or music, this will go to speaker. That is typically the block diagram of a radio receiver, right. So that is a typical radio receiver. Yes, I think there was a question there.
Sir, could you please explain that amplifier?
IF amplifier?
Yes.
Basically what we are saying is, because the IF amplifier is at a fixed frequency, what is the fixed frequency? Omega IF, right. No matter what the incoming signal frequency is, the same signal is now available at omega IF, right. It's much easier to design an amplifier of fixed frequency with the properties that you want, namely selectivity, high selectivity and high sensitivity. These are very easy to build in a amplifier of fixed frequency rather than an amplifier of variable center frequency, right. So you can make it highly selective in the sense that two signals which are separated by, suppose this fellow here, the RF amplifier here does not do its job well, right. So two signals which are close by will come out here. It will not be just omega c, but a few other frequencies which are close to omega c will also come out here with some amplitude. So they will also be present here, but their frequencies will be slightly different, because they are not exactly at they are not exactly removed from the local oscillator frequency by omega if, right. So these will also be present here, but this IF amplifier will be able to reject them, because it is designed to only accept the true omega if, right. Any other close by frequencies which are not of interest, it will be able to reject them. You can make it frequency selective enough to reject all close by signals which are not rejected by the RF front end. Okay, that is basically what I was saying. That is what is meant by selectivity. I can make it highly selective, right, and highly sensitive by providing a large gain to it. Okay, so this is roughly the block diagram of a radio receiver. There are a few features which I have not mentioned. For example, can you give me some idea of some problem which has not been taken care of in this picture? No, image frequency is something I am coming to, right? That has to, yes, I will come back to the image frequency issue. That is an important issue. Yes. Any other thing which has not been taken care of? Please speak a little loud. I can't. No distortion. We said if the power amplifier design is done properly, there will be no distortion. Right? Any other thing? Noise we already discussed. Okay. Let me tell you something. We said that the signal this has to be highly sensitive, right? Which means you are saying that this gain should be, the gain of this amplifier should be large. Can that create problems? The gain is large. Suppose the signal that is coming in is already very strong and you have a very large gain sitting here. What can that do to the system? The amplifier will go into saturation, right? So we don't want that situation also. So there are other things that you require in the receiver. For example, there should be some mechanism to automatically control the gain depending on whether the incoming signal is weak or whether it is strong, right? Typically that is done by taking a feedback from here, right, by looking at the message signal and seeing how strong it is, right, and use that feedback to modify the gain of this amplifier. So there is a gain control signal which is generated from this through some processing, right. So gain control is carried out and the IF amplifier gain is reduced or increased depending on whether you are working with a weak signal or a strong signal, right. So there are other such nice features that we like to include in the design of the filter. Actually the receiver is quite complex, right, if you include all these things. The principle is very simple, but the details become more and more complex as we try to include more and more features in the receiver, right. So but broadly speaking, this is what a radio receiver has to do. Okay. Yes, somebody mentioned a few minutes ago the problem of image frequency. That will be a problem, right. So let us look at that problem. So to appreciate that problem, very clearly let me draw a picture here. Let us say your desired signal is at frequency omega 1, which is the carrier frequency that I am talking about. This is the, I am plotting this in the frequency domain. So this is the desired signal. It has this spectrum. I have just arbitrarily plotted some spectrum. It is not very important. The shape I have arbitrarily drawn. So what will your local oscillator frequency be chosen to be? Your omega LO will be omega 1 plus omega 2, which is basically omega C plus omega IF. It could be minus also. Omega C minus omega IF also is permissible, but we will see whether plus is better or minus is better in a few minutes. And after the mixing of these two, this signal will be translated to omega IF, right, which is typically a lower frequency than the incoming carrier frequency, right. So this message signal is put back to omega IF. So this is your omega 2. Omega 2 is now equal to omega IF, right. Now it is quite possible, and this is, of course there will be component at omega 1 plus omega 2 plus omega 1, right. So there will also be component at 2 omega 1 plus omega 2. When you are mixing omega 1 with omega 1 plus omega 2, you will have a component at omega 2 and another component at 2 omega 1 plus omega 2. However, this is not of interest. This will be removed by the filter following this band pass filter, the IF filter. This is what you want. This is the desirable thing. The undesirable thing is the image frequency. What is the image frequency here? Omega 1 plus 2 omega 2, right. So, let us say it can be somewhere here, and let us say there is another message signal present there. The second signal, there is a radio station whose center frequency is omega 1 plus 2 omega 2, that means omega c plus 2 omega if, right. Suppose there is a second transmitting station which is transmitting at this frequency. When this mixes with this local oscillator, what will this produce? It will again produce an output which is centered at omega 2, right. So, we will get this signal at omega 2 which is at omega if. So, this is the desired signal and this is the image frequency signal. Now, I should not use IF, so image signal, right. And these two things are coming in together into the IF amplifier because IF amplifier will see this spectrum as well as see this spectrum at the input. So, both the signals will go in and now you will have a problem, right. There is no frequency selectivity.
So why can't we filter out this omega c
That has been done.
at the receiver?
The radio frequency.
Sorry, why can't we?
Filter out omega c at the receiver.
So it will filter हो ही जाएगा.
Mix it.
No, you are absolutely right.
So वो तो पहले filter
So, basically the important point that you have made is the correct point. What we need to do is to make sure while this filter may not be very selective, it should at least be selective enough to make sure that while it is passing omega c, it does not pass omega c plus 2 omega if, right. So, therefore, the selectivity requirement of the RF filter, it is still there, but it is a very moderate selectivity requirement. What you are saying is the two carrier frequencies which are separated from each other by 2 omega if be separated at the RF stage itself, and that is the solution your friend was proposing here, which is the right solution, right. So, the image frequency will be taken care of, will not be a problem if we make sure that your radio frequency filter that you have here, the radio frequency amplifier that you have at the input stage is at least slightly selective to make sure that when it is selecting omega c, it rejects omega c plus 2 omega if, and typically 2 omega if is fairly well separated from omega c plus 2 omega if is well separated from omega c. So, that separation should not be a major problem. Realizing an RF filter with that kind of selectivity should not be a major problem, right. To see things more specifically, let us take some figures. For typical radios that you use, the AM radios or whatever that you use, let us talk about the AM radios. The band frequency, the typical AM band that you work with is 540 kilohertz to 1.6 megahertz, alright. And a typical convenient IF frequency to use, intermediate frequency to use is 455 kilohertz. Excuse me. So, what is the separation between any incoming signal frequency and its image frequency?
900. 10.
455 into 2, right. So, omega image minus omega c is of the order of 1 megahertz, right, almost 1 megahertz. 500 into 2 is 1 megahertz. What does it mean? Anyway your incoming signal frequencies are in this range, 540 kilohertz to 1.6 megahertz, which means for this particular situation the RF filter need not be tuned at all. It does not require any frequency selectivity, and still because the bandwidth requirement, the image frequency separation is quite far in this case. Image frequency will not typically cause a problem because most of your transmitting stations are lying in this range, right. So even if the worst situation will arise if your omega c is 1.6, right, or let us say omega c is 540 and omega image will be 1.54, right. Now separating, if you so you require a very moderate selectivity, hardly any selectivity. You are saying when the 540 kilohertz signal is coming in, the 1.54 megahertz signal should not be allowed to pass through the RF filter. This is hardly an issue. It can easily be done. Yeah? Designing such an RF filter which is tunable and providing you this kind of selectivity is not an issue. So
But why don't we use higher IF frequency? So then we won't need any kind of selectivity.
you are making your job more difficult in that case. You don't want to go outside the band of interest. You must keep well below, because it's much easier to build amplifiers with high gain and cheap components at lower frequencies than at higher frequencies. You don't typically intermediate frequencies will be much less than the band of operation, right? That will be the answer to this. So in this case the RF filter need not even be not required to be highly tunable. Highly selective, or for that matter even tunable, at least in this case. Almost without tuning you can take care of the effect. Okay. Any questions? One last issue in this connection. Let us look at the local oscillator requirement. The local oscillator, we could choose a frequency which is omega c plus omega if, or we could choose a frequency which is omega c minus omega if. The question is there any preference for any of the two? What would you like to say on this? Which one would be better and why? Okay. To understand that issue, let us consider the same band, 540 kilohertz to 1.6 megahertz, right, or 1600 kilohertz. If you choose this, if you choose omega c minus omega if, what is the range of frequencies that the LO is required to generate? Right. It will be 540 minus 455, which will be, let us say, about 85 kilohertz. Right, and 1600 minus 455, which will be about 1145 kilohertz. Right. If on the other hand you choose omega c plus omega if, then the range of frequencies would be 995 kilohertz to 1600 plus 455, which is 2055 kilohertz. Right. So the issue of whether to choose this or to choose this really boils down to whether this is better to use or this is better to use, or this is easier to build or this is easier to build. What is your gut feeling about it? The upper one or the lower one? Which oscillator you think will be easier to design? Lower one. Why? The ratio of the frequencies that you need to vary it over. So you want a tunable oscillator here. A variable frequency oscillator is what you are looking for, and the ratio of frequency is almost just 1:2 here, whereas here it is 1:20 almost, not 20, about 13-14, right. So the ratio in case 1 of the two frequencies, this divided by this, is of the order of 13 to 14, right, whereas in case 2 it is almost 1 to 2. basically of the order of 2, right? And it's much easier to design oscillators where the tuning range or the variable frequency range has a smaller ratio than a much larger ratio, and that's why typically you go for the higher local oscillator frequency rather than the lower local oscillator frequency, and that's in fact the reason why it is called a super heterodyne receiver, right? Heterodyning, heterodyning is mixing, but you are mixing with a local oscillator which is at a higher frequency, and the name super heterodyne actually comes from there. Besides, if you wish, you may say that it is super heterodyne because it does a superb job, right? But that's not the reason, right? Yes, please.
So if the lowest value of omega c and omega if are comparable,
If the lowest value of
omega c and omega if are comparable, then 2 omega c minus omega if will lie near omega if, and it can create a problem. We can look that also.
but again you can see that if you don't require very large separation. Let's see, 2 omega c, let's say 2 omega c would be 2 into 540 minus 455, doesn't create a problem because the separation is still separation between these two is still of the order of 450 kilohertz, right? That will be taken care of by the IF filter.
But the omega if is also at 450. So in case
No, omega IF is at 450.
So one signal is at omega if and the other is at 2 omega c minus if.
Let's see the difference. The difference is still huge. This is about 1180 minus 455. Whatever, it's quite large. Whereas the IF filter, which is centered at 455 kilohertz, where the desired signal lies, has a bandwidth of 20 kilohertz or so, right? So it's not an issue. Think about it. If you still have a question, we'll take it up.
But we should keep in mind that omega if should be lower value than the minimum of that.
If you have a peculiar situation, then certainly you should guard against such a situation, but it's not going to arise in this application, right? You must choose a value of IF which satisfies all these requirements, right? That is of course true. So IF has to be carefully chosen, and the value of 455 kilohertz is a standard value for most radio receivers, right? It's a standard value that is used. It's important to do such standardization so that you can go in the market and buy components, right? You cannot, if somebody decides to use one intermediate frequency and some other person wants to design some other carrier intermediate frequency, it's going to be very chaotic. You can't go to the market and buy components and build a receiver that you want to build, right? So that's something that standardization is always a required thing. Okay, now we have enough time just to take up one small issue in some detail, and that is the practical realization of the devices which we have taken for granted in all these discussions, right? These devices are the mixers, the multiplier, the modulator. We call it by different names, but essentially it's a multiplier, right? We have had occasion to discuss these briefly elsewhere, but let's spend some time on, if it's a very small discussion we like to have on how do we realize these things. Why? Because I wanted to give a brief idea about these things in this class is the reason why I put that etc. in the title of my lecture today. That is super heterodyne receiver, etc. Right? So the etc. was because I wanted to spend some time on this. Now I'll just have a very brief discussion here. One is we can realize these kind of devices using nonlinear elements. Right? For example, the nonlinear elements that basically what do we want to do? We want to multiply two signals, right? It could be the message empty with the carrier, it could be the incoming carrier frequency signal with the local oscillator signal, right? These are the kind of things we want to do. How do you multiply? We know how to add signals, we know how to subtract signals. Addition is the multiplication is possible by using nonlinear elements in your circuit. Using linear elements is impossible to do that, right? For example, you could have nonlinear IV characteristics of some device which you could exploit, right? For example, you could have a device whose current voltage characteristics are of this kind. In which case, if I choose my input voltage V1 to be the sum of the two signals that I want to multiply, right, then because of the nonlinearity I will get some product terms. The only thing I have to ensure is that they should, along with the product terms, there will be lot of other terms as well, right? So what we have to ensure is that it is possible to separate out the desired product term from the rest of them, right? So nonlinearity will produce product terms or the desired product terms typically they can be separated out from the others. By appropriate filtering, right? If it's possible to do that, you do that. So this is one mechanism of realizing these multipliers or these modulators or mixers. Typical devices which will exhibit these characteristics are PN junctions of diodes and transistors, right? So most of the mixers and modulators can be realized using the conventional diodes and transistors, right? I will not have time to go into actual circuits here. I would like you to look it up yourself, okay? I will give you a reference for this in the class next time.